Thank you very much for giving me this chance to present our recent work on this boosted Diurnal effect of Sub-GeV dark matter. And this work is with these collaborators. So currently, we know that dark matter direct detection experiments kind of like approaching the neutron flow, especially in these lower parts with the coming like Panax photon or xenon anton experiments. We can already touch this part, and with future even larger experiments, we can cover almost all the parameter space, and it can explore a large part of the parameter space for some, for example, supersymmetric models. So that's very impressive. But the thing is, this only covers several orders of magnitude. For dark matter, the mass range can be pretty large, like up to like 80 orders. And especially for this kind of like sub-GeV range, the constraint is not that stringent. So we need to think that how to get to improve this kind of this region. So the basic idea for direct detection experiments is something like catching the rabbits with the tree. So dark matter is kind of like a rabbit. It comes to hit the tree, and we just see whether the tree would shake, and use this to infer the existence of dark matter. But unfortunately, these dark matters, they are quite sleepy. They don't move that quick. So non-relativistic cold dark matter. So that would lead to a huge problem because the direct detection experiments always has a threshold, energy threshold. So for especially the light dark matter, it wouldn't provide that large recoil, then we cannot see it. The question is how to go beyond. Several ways. One is from the experimental side. We can probably use smaller trees, then the effect will become larger. For example, we can use the electron inside the atom, or we can use some new concept detection methods. For example, the condensed matter methods, superconducting stuff, with a very narrow energy gap that can give us a much lower threshold. And in addition to that, we can also think from the theoretical side. For example, can we get faster rabbits, get relativist type dark matter? One way is from the heavier dark matter. If the dark matter existing, the one existing in the universe is heavy, but they can decay or annihilate into lighter ones, then the light ones can move faster, and then we can give this kind of detection. But that's based on a lot of model assumptions. First, we need to have a multi-component dark matter theory, and they need to be able to decay or annihilate. Can we get a different way? So with a minimal assumption, that is possible. So this is the basic picture. If we are able to detect dark matter, that means the dark matter can interact with the nuclei, here, the rabbit and the tree. And then we can just reverse the process. We can use some stick, which is made from the wood, and in principle, it can interact with this rabbit. We just isolate it. And this kind of process actually can happen very naturally in our universe, because in our universe, there are a lot of, sorry, I think I lost one page. Okay, anyway. So basically in the universe, we have cosmic rays, and cosmic rays is similar to the detection target, the nuclei. And cosmic rays, they move much faster. And if dark matter interact with nuclei, then it will lead to natural acceleration of it. And the basic picture is something like this. This counts the production rate of this cosmic ray dark matter. So here is the cosmic ray number density, and here for simplicity, we assume some constant cross section. So in this integration, it has kind of like a Flag distribution for the kinetic energy. So T maximum in the denominator, and the integration is just from the minimum value to the infinity. Of course, we also need to take into account the form factors. So finally, if you can get this kind of like accelerated spectrum. So from the top to bottom, the mass would increase from like 1 MeV to 10 to 100 MeV and 1 GeV, 10 GeV. And you can see that the dark matter energy can be quite large, something like 10 to minus 3. That's the MeV scale. And due to the detection threshold, there is some limit here. But anyway, if you can compare in this subplot, we can see actually it's moved to the higher end, and the flux actually can be sizable. And if we go to focus on those above the threshold, you get this kind of plot. Here we have more features to see. First, with increasing dark matter mass, the flux will decrease. This is understandable because in the denominator, there is the dark matter mass. So it's kind of like inverse scaling. And another thing is with the lighter mass, the spectrum would shift to lower side. So you can see that on the left-hand side, the flux would increase. This is because this kind of kinetic range in this denominator, we have this induced mass. And this induced mass is inversely proportional to this dark matter mass. And with the lighter dark matter mass, the induced mass actually becomes larger. And this would effectively suppress the allowed range for the accelerated dark matter particle. So with the smaller mass, the dark matter its kinetic energy would be suppressed to the lower part. So it would increase scale, but it would decrease at the higher end. And this is because with heavier dark matter, it's much more difficult for the cosmic ray to accelerate it. And another interesting feature is the cosmic ray and the dark matter, both of them have a higher distribution probability around the galaxy center. This would lead to a very interesting phenomenon. This would become some anisotropic distribution. And most of them would come from the galaxy center. And another thing is to detect them, the CLDM should pass through some Earth matter. And the Earth is rotating around its axis. And depends on the time, it needs to pass different distance. And if the cross-section is large enough, then during this process, the cosmic ray boosted dark matter would scatter with the Earth matter. And this would transfer some energy from dark matter to the ordinary matter. And if it scatter many times, a lot of energy would be lost. So the flux would shift to lower energy. And this would naturally lead to daily modulation, the diurnal effect. Before going that, I would mention that the osmotic profile is different. If it cross the core, not just the distance would becomes longer, but also the matter density would becomes larger. So it would have larger chance to scatter. And this shows the effect of attenuation. So this black curve is the original one, coming from the space before arriving to the Earth. And depending on how much distance it needs to pass, I use the Nadia angle to denote it. For example, if it's 30 degrees, then it needs to pass very long, more than 11,000. So it becomes significantly attenuated. And with shorter distance, for example, even the horizontal one, it needs to pass something like 160 kilometers for a detector 22 kilometers underground. So that's not a small distance. It would have a sizable effect at the high end. And for 60 degrees, it also the effect is very significant. So this one thing changes the spectrum, the energy distribution. Another thing is changes the event rate. This is the boosted recoil. You can see that at the detector, the recoil is quite large. So I plotted this one, those above the threshold. The threshold is something like 3 kV. And for different paths, it would collect different rate. And this is the Diurnal modulation result. You can see
2 minutes
that.
left for your talk.
Okay, thanks. During these 24 cycle hours, you can see that it has this kind of modulation behavior. And for those at the bottom, it's kind of like close to zero. And this is because of it needs to pass the longest distance. And if the galaxy center would pass above the detector, the dark matter would come from the head. And this one, it has a very large chance to survive. Of course, finally, we need to take into account the threshold effect, but still the modulation effect would be present. So we also studied the influence of the dark matter profiles. As we know, in the galaxies, the dark matter density distribution can have a large difference around the core. Fortunately, this core size is not that large, and it would have some effect on the modulation. You can see between different curves, if we change the distribution for this part. It's just the slightly changes it. The big picture is still maintained. Okay, so summarize what I talked about. So currently we have very good constraint parameter range around 10 to 100 GeV scale. But how about the Sub-GeV? This part is not that well constrained, and we need to find different ways to do that. And we found one way based on the minimal assumption. As long as the dark matter scatter with the nuclei, it's not just happen inside the detector, but also it would happen in the galaxy. The dark matter, the non-relativistic dark matter would be naturally accelerated by the cosmic rays. And there are two major features. One thing is the energy, the recoil energy can be large. So we can try to see the recoil with, for example, 100 kV, that kind of scale. And another thing is if we can see the time modulation within one day, the cycle day, it will have this kind of periodic oscillation. Okay, thanks.